welcome back to our series again on cosmology and astrophysics. I'll put the links for our previous videos in the description below. We have till now we have covered up topics about cosmology, baryonic acoustic oscillations, and how did the universe form from the initial moment, how did all the elements came up, what do we see as the cosmic microwave background and everything. So now that we have seen it all, from there on there is one track which I'll put as a separate video series, which is on cosmic structure formation, how did we see, how did the universe form, the structure of the universe form from there. So are we still keeping that homogeneous and isotropic nature of the universe, and what caused the structure that we see here today, right? I mean, if you look at it, if you zoom out, if you actually go and search for this was an old video and it's a super famous video. I'm pretty sure there are a bunch of websites also which have interactive content around it and so on, called the power of 10, where you can zoom out. So if we start zooming out, right, from if you start from say here, Earth, in our thing, 1 meter scale, you zoom out, zoom out, zoom out, you'll see Earth. You continue zooming out, you'll see the solar system. You continue zooming out, you're going to see the Orion arm of Milky Way galaxy, where we are a part of. We are in the outer edge of the outer section of the Orion arm of the Milky Way galaxy. You go out, you'll see the whole of Milky Way galaxy. You zoom out even further, you'll start seeing the nearby galaxies like Andromeda and Whirlpool galaxy and so on. And all these galaxies will come together in what we call as the Virgo supercluster, the galactic neighborhood. And if you go even further, there is some really interesting pattern that you will see in the universe, which we call as the cosmic web. It is actually an interesting pattern where you will see clusters of galaxies once a while, and there will be they will all be interconnected through some intergalactic material, or there will be some lonesome galaxy in between, and there will be voids in between. So there are voids where there are absolutely nothing, and all the galaxies will be accumulated in one place. So this is what we call as the cosmic web. And I'll come to this in a later series because this demands a series on its own. So I'll come to this entire discussion on a later series. So for now, I think I just wanted to take it even further down. That is my own personal field, the topic that I really like, which is star and planet formation. So I want to go further down there, and I want to explain to you guys what happened. I mean, instead of more than on the galaxy formation, I wanted to go into the star formation, because that is actually, it plays a significant role in the history of our universe. Not just the stars that you see around, but historically, how did the stars end up the way it is? Now, if you had seen our earlier videos, I would have explained about nucleosynthesis, right? Now, in the Big Bang nucleosynthesis, if you go back to the past, right, if you would basically see that the universe was primarily hydrogen, and there was enough energy to fuse a little bit of hydrogen to form helium. And that helium also combined a little bit more, and you had a little bit of lithium and a little bit more heavier metals. But okay, I have to clarify this. So in this entire series, there are three main aspects that I will say. So in any astrophysics textbooks, if you go and check out say the distribution of elements in anything, right? So if you look into the composition, there are three main aspects that we say. One is hydrogen, which we mark it by X, helium, which we mark it by Y, and the other ones are what we call as metals. I know this is a vague term, but in astrophysics, anything that is not hydrogen and helium is metals for us. I know it's a super broad assumption, but this is how it is. Because majority of what we care about, right, if you look at it, in most of the cases, even if you look at the sun, 70% is hydrogen and about 28% is helium, and about 2% of the rest of 2% what makes the rest of what we see, like carbon, nitrogen, everything is just this 2%. So for us in astrophysics, we call everything else as metals. So typically, like yeah, this in this series you'll understand why this is important, because these XYZ plays the vital role of how we ended up here and why the universe the way it is. There's actually an interesting aspect to it, not just in astrophysics but also in physics. If you actually like look into all the fundamental constants in physics, right, be it like the Planck's constant, the speed of light and whatever, if you change the value even by a tiny fraction, the universe wouldn't be the same the way it is today. We wouldn't exist. The stars wouldn't be the same way. Even physics wouldn't be the same. Even if I change like h, the Planck's constant, by a tiny fraction, if you actually try take any of the physics equations that you work with, right, Boltzmann constant or even Planck's constant, all these are absolute, like there are relative constants and absolute constants. I'm talking about the absolute constants like speed of light, Planck's constant and so on. If you like try solving the same problem by tweaking Planck's constant a little bit, instead of 6.67 you make it 7.77, let's say that, and try doing the math again, you will get a completely different universe in your picture. You will, the results will be spellbounding. It won't even be near reality. You won't even, so that's why it's wrong, right? I mean, you won't grasp that it is wrong. So the universe is the way it is because of all these fundamental constants, and not just the fundamental constants but the composition of all these material. How did this composition evolve into this, right? Now if we look at our solar system, our sun has this composition. Why is it so? If I change, let's say hydrogen is now 2% and I have a lot of 70% of heavy metals, the world is completely different, because if hydrogen is only 2%, well, you don't have enough hydrogen to like fuse, so nuclear fusion will fail in the stars. If nuclear fusion fails, like, well, the sun won't work. If the sun doesn't work, imagine the life around our universe, right? Imagine the life on Earth. It's impossible to have life on Earth without sunlight, right? So if the sun, like, even if I change the fraction, right, everything in the universe just breaks apart. So that's why these numbers are super critical, and that's why like all these fundamental constants, as we say, are super critical on why they are the way they are. So this is like a whole different aspect of physics, and even in theoretical physicists would love to talk about hours on this, but okay, we get back to our astrophysics. So I just wanted to share this thing, because now that we saw till like where we are, right, like the baby picture, the first 300,000 years of the universe, we have reached to a certain age, the universe has reached to a certain age. Now, okay, then slowly structure started forming in the universe. I explained to you just briefly about the cosmic web. But more interestingly, like, okay, now let's skip a few, not millennia, but few millions or few billion years later to our current age, right? We calculated the age of the universe in our previous video, where age of universe from Hubble's law, age of universe is 1 over h0, 1 over the Hubble's constant, which was around 13 billion years. So our universe is about 13 billion years old. So now the cosmic microwave background was around 300,000 years. So this was like the baby picture of the universe. This was what we call as the last scattering surface. So this is the moment when the universe basically, like, the light and matter decoupled, as in when a photon is emitted, the mean free path of a photon was long enough that the photon can escape before being reabsorbed by another atom. So this was the moment the universe expanded enough so that the light can escape. Before that, the light was just trapped in there. So this is why we say that the cosmic microwave background is the baby picture, because this is the oldest picture of the universe. You can't take a picture older than that. And while I say oldest picture of the universe, right, the way it is that, like, this is an interesting aspect. I think I would have mentioned it in my previous videos. The further you look in space, the more back in time you go. That is, say if I look at an object, the nearest star, Proxima Centauri, which is about 3 light years away. If I look at Proxima Centauri right now, I'm looking at how Proxima Centauri was in, now this is 2023, how Proxima Centauri was in 2020. If someone is there in Proxima Centauri and looking at us right now, they would just see that we are going through a global pandemic and people are dying. They don't know that we have survived this pandemic, we actually came out of it. They wouldn't see it because the light has taken 3 years from us to go there, and the current light that they are receiving right now in Proxima Centauri is the light that we emitted, like that we reflected during 2020, during the peak pandemic. So now if I go further 300,000 light years, I'm gonna start seeing no, not 300,000, 13 billion minus 300,000, so about 12.7 billion light years back, I'm gonna see the baby picture of universe, the cosmic microwave background. So if I go to, so it's about 12.7 billion years in the past. So now let's skip this, all this moments, and now we come to our present thing, or maybe like about 4.5 billion years to the past. All these numbers sound super relatively young, right? When I talk about a young star or a baby star, this is just about 500,000 years old. Keep in mind, we are all just like, you know, in our teens, maybe in 20 to 30, 30 to 40, 40 to 50 years. These are baby stars which are less than a million years old, few 100,000, few lakh years old. So our sun is about 4.5 billion years old. The way we found out was, okay, I know that what was the initial conditions in which the sun formed, and now if I look into the composition of sun, I can figure out, okay, how much of fuel did it extinguish, and that means if it has been burning at this rate, how long did it take for us to reach this point? It's about 4.5 billion years. So let's roll the time back by 4.5 years, 4.5 billion years. So we are at 13 billion years today. So let's go back by 4.5 billion years in the past. So now how did our sun form, right? 4.5 billion years ago, it was what, 8.5 billion years from, the universe is 8.5 billion years old. Now by this time, the universe wasn't just hydrogen, helium. It had a lot of other materials. There were like a lot of the stars, which I'll come to in a bit. Now, how did a star form, and how did the planets around the star form? Does all stars have planet, and are all solar systems same? Are they similar? This is what I want to answer in this in the next set of videos. I want to explain to you how does all these things string together. So okay, so now if we start, right, now at this point there are enough metals. By metals, again, I have to reiterate, it's anything above helium is a metal for us, okay? Now, why am I stressing on metals? The reason is thermodynamics. The whole point is, now the universe, if you go out and look at the night sky, probably not right now, but in winter, which is like in a few months, say in a couple of months from September or October, if you look at late night sky, you will see the famous constellation Orion, 3 dots. And below the 3 dots, you will see something fuzzy below it. That's the Orion Nebula. Now, these are basically molecular clouds. By molecular clouds, what I mean is these are just gas pockets around the universe. How are these gas pockets there? Well, it could be remnants of previous stellar activity over there. So there could be a star. Typically, a star forms out of these molecular clouds. These clouds like end up, so when you compress these gases together, right, at high pressure, like you pack it all in at a certain point, what happens is you would have compressed the gas to such a level that the pressure is super high, and if you remember from thermodynamics, if pressure is high, the temperature goes high. Right? So the temperature goes high. Now, if I build enough pressure, the temperature will be super high for me to start kicking out electrons from a hydrogen atom, and the hydrogen nucleus can start fusing with one another. So nuclear fusion will start. Now, this moment in astrophysics is what we call as virialization. Virialization is basically the moment at which a star is born. So what makes a star is because it can fuse materials together inside it and it can produce energy out of it, right? Just like what is the main role of our sun, right? The main role of sun is to fuse hydrogen and all the materials and to basically provide us with light, heat, whatever you call it, right? Now, and also of course gravity to hold us together. So the thing is, okay, these molecular clouds collapse, they form, they compress, and as the pressure builds up, the temperature goes up, and as the temperature goes up, the hydrogen atom starts to fuse with one another, and this fusion ends up, like once the fusion starts, well, voila, we have a star with us. But okay, how, now you might have a question, okay, so what compressed this gas together? I mean, you know, a gas can't just randomly start compressing, right? I mean, if I have to compress something, I need to put on some work, because nothing just happens without work, right? Like, I mean, I need to compress it together. So what caused this work? So typically what happens is, again, like, let's go back to thermodynamics again over here. As a gas starts to cool down, as it cools down, it basically, now the hotter the gas it is, the more expanded it is going to be, right? The volume is going to be high as the gases are hotter, because again, the higher the temperature, the more the pressure it is, so it will be more outwards. Now imagine as it starts cooling down, like a gas can cool down by a lot of different things. Say there can be a metal in there. The metal can basically, now what is energy over here? If we look at it more like as a light, right? It can absorb these photons, and you know, it can act, it can like all these metals and heavier elements can absorb a photon, move an electron to a excited state and come back to its original state and whatnot, and it brings it, like as the energy is like getting reduced, the temperature will also go down. So these actually plays as a really good cooling agents, the metals and all the heavier elements, they start cooling down. And this is what, if you look into, like, you can actually search, or I'll put the image over here, what we call as stellar nurseries. Now these stellar nurseries are basically places where there are like a lot of what we call as dust. Dust is nothing but carbon and silica and so on. Now all these dusts, like you will see them actually, like say there is like this stellar nursery, or like, you know, you can search for Eagle Nebula, for example. Now all these stellar nurseries act as like local cooling spots, if I want to put it that way. Like, you know, that's where like the temperature of the universe starts cooling down over there locally, and the gas will now slowly start to contract inwards, okay, because now the temperature is down, so it will start contracting inwards. Now as it contracts inwards, imagine this is like few million, like all these molecular gas clouds over there are humongous as compared to sun, right? Or an average star, they are few million times, few 100,000 times bigger than the sun. So imagine like a molecular gas like that collapsing. Now if I pack up all these material into a small area, it is going to build its own gravitational potential. Now the battle begins. The battle is between gravity and thermodynamics. So that's where the battle begins. So now with this, I'll stop this video. I just wanted to give an introduction. In the next video, we'll start discussing about this battle. What happens? How did this battle end up forming a star? And also about planet formation. And also how did these cooling happen in the initial universe, where we didn't even have much of metals back then. Right? If you go back to my earlier videos, the universe was primarily hydrogen and helium. Helium was very little fraction, it was just hydrogen. Hydrogen atom by itself can't do all these cooling, it just has one electron, so it can't do all these fancy cooling stuff. So how did we cool the universe, and how did the stars form then? So let's go with that, and yeah, let's start with that. So thank you, and see you in the next video.